Okay, welcome back to Forces Part 2. In Forces Part 1, we looked at Newton's laws, and we looked at two types of forces, gravitational force and the normal force. Gravitational force, we looked at the universal law of gravity and simplified that equation so that we could calculate just the force due to the Earth or calculate our weight, which is the most common gravitational force that we care about in this class anyways. The other thing that we looked at is normal force, and we'll look at normal force more in this video after we look at a few more types of forces. And then after this video, there are two videos where I do problems, so you certainly are welcome to look at those and get a sense of how we apply Newton's laws and how we apply these forces in situations to analyze motion. But the other forces that we have to talk about both are frictional forces. In general, frictional forces are forces that oppose motion, right? So we automatically know the direction of these forces, like gravity, or at least gravitational pull of the Earth, we knew the direction of that. It's always down, the Earth pulls down. Frictional forces, we always know the direction of those too, right? The direction is always the opposite of motion. Or if it's not moving, then it's the opposite of the desired motion. So we can get the direction without doing too much. Now, for friction, there's two different types of friction. There's slide-in friction and static friction. Slide-in friction is friction when an object's moving, or more importantly, when an object is sliding, when one surface is sliding over another surface, right? So one surface is sliding over another surface. Because we could have something moving and that's not happening. For example, if you're driving a truck and you have a box in the back, if that box isn't sliding around in the bed of the truck, it's not sliding friction. The box has to be sliding with respect to the bed of the truck. So one surface moves over another surface. There we go. So there has to be motion between the two surfaces. And then static friction is kind of the opposite of that. There is no motion between the two surfaces. The two surfaces are locked together, right? So it's no motion. And again, that doesn't imply it's not moving. That's most of the time, right? Most of the time we're dealing with static friction. The object that we're trying to move isn't moving. It's static friction. So no motion of one surface over another. But there are places where there's situations of motion where it's still static friction. Your tires in the road, that's static friction. Why? Because the tire's not sliding on the road. At least I hope not, because that's when you're in trouble, right? But the wheel is locked in with the road. So the part of the wheel that's touching the road is not sliding over it, right? So that's still a static friction, even though you're moving. Just most things around you, if they're not moving and you try and push them, the first thing you have is static friction. You have to overcome it to get it moving. No motion of one surface over another. So we have some differences between the two of us. And it's important to understand the difference because they are two different frictions. And one of the things we know, if you've ever pushed something, that static friction static, tends to be greater than slide-in friction, right? It's harder to get something moving, but once you break it free and once it starts moving, it's a little easier to keep it moving. So we know that even though they're both friction, they have to do with these surfaces. When something's at rest, it's harder to break it free and get it moving. But when something's already moving, it's easier to keep it moving, right? All other things being equal. So static friction tends to be greater than slide-in friction. And that's important, right? That's how rear anti-lock brakes work. I'm not going to go into it now, but you could certainly look it up and see, right? Rear anti-lock, or rear, not necessarily rear, but all anti-lock brakes, I should say, have to do with the fact that they let the wheels roll for a moment, so that static friction is the friction that's between your tires and the road. Once your car goes into a slide and you're in the slide-in friction, it lets the wheel roll again for a minute, so we're back to static friction. Because static friction is stronger, it's going to slow the car down quicker and more safer. So there are some differences. Now, if we just focus on slide-in friction. So first we look at slide-in friction. And if we think about it, if we think about the things, because we've all pushed boxes, made them slide or move things around, what would be the things that would change the amount of friction? What would be the things that make it harder or easier to push something around? Well, the obvious one is we could change the surface we're pushing it on, right? If it's a smooth ground, if it's ice, it's going to be easy to move it. If it's something like sand, it's going to be hard to move it, right? So as we change the surfaces we're trying to push the box on, we can make it easier or harder. Therefore, we could change the frictional force. But we could also change the surface of the box, right? If it was a different material of the box, and it could, again, make it easier or harder, right? If we made it out of leather, it would kind of stick. It'd be hard to move. If we made it out of hard plastic, it'd be easier to slide it. And, we can go all day finding different surfaces, but the surface of the box also matters. So that's what coefficient of friction is. Coefficient of friction is the measure of the smoothness or roughness between two surfaces. So we can look up these values. You can just Google them and you can find them all over the place, but there isn't a coefficient of friction for one surface, because that's not what it's measuring. It's measuring the interaction between the two surfaces. One surface is sliding over the other. So you could look up the coefficient of friction for, let's say, wood on concrete, and it's out there, right? You can't get a coefficient of friction for just wood. That's impossible, right? And you can't get it for just concrete. That's impossible, right? But you could definitely get it for wood on concrete. You can get it for rubber on concrete or tire tread on concrete, right? We do all these different things. As a matter of fact, tires, right? The whole point of tires is to have a high coefficient of friction. That's what the grooving's for. That's what the shape's for. That's what material's for. It's to increase this so that it's a very rough surface and it interacts very well with the road, so there is no slippage. Now, we're not going to write this out every time. Coefficient of friction is represented by mu. Mu is the symbol for coefficient of friction. The other thing that matters if we're trying to push a box is, well, it could be how heavy it is, right? If we have this box and we put a lot of mass in it, therefore there's a high weight to it, that box is going to be harder to move than a box that has low mass to it, and therefore low weight, right? So the weight of the box certainly makes a difference. And if we don't change the weight of the box and we just push down on that box, well, then that would also make it harder to move, right? If you're in a situation where, like, someone's trying to pull something away from you and you just slap down and push down on that object, makes it harder for them to pull it, right? So both of those things, changing the weight and just applying a downward force or an upward force, right? These things change the normal force, how hard the ground has to push up. So if we make the ground push up a lot, there's going to be more friction, right? And we can make the ground push up a lot by increasing the weight or just pushing down. So it has to combat multiple forces and push up more to cancel them all out. So these are the two things that affect slide and friction. So I can say slide and friction is equal to the coefficient of friction times the normal force, where the coefficient of friction is a number that measures how smoothness or roughness the two surfaces are that are in contact with each other. And the normal force is what we talked about last in the first video, which is how hard the surface has to push up to stop you from falling through it. So there is one equation, the equation for slide and friction. Right. And static friction, friction that's present when an object's not sliding, it's really the same things, right? We still care about the measure of smoothness or roughness between two surfaces. The two surfaces matter if we're trying to get something moving, certainly. And how hard the bottom surface is pushing up still matters, right? More weight means it's harder to get something moving. If you push down on an object, means it's harder to get it moving, right? So the same statements can be made for static friction, except we already know that static friction is greater than slide-in friction, right? So even though they have the same basic components to them, they are different. So first of all, let's put the equation for static friction, right? Static friction, and this is where it becomes different, static friction is not equal to, it is less than or equal to the coefficient of static friction. So it's the same thing. It's a measure of smoothness or roughness between two surfaces, but it's the measure of smoothness or roughness between two surfaces when the surfaces are not moving. And then the normal force. So there are some differences. One is this was the coefficient of friction. We could even say it's the coefficient of slide and friction. And this is the coefficient of static friction. And we tend to just call it that. And the other difference is this is a less than or equal to value, or this is an equal to value. Slide and friction, if the object's moving, there is a certain amount of slide and friction. And the only way to change that is to change the surfaces or change the normal force. Just by moving fast or moving slow doesn't change the slide and friction. Slide and friction is independent of how it's moving. It's just dependent on these factors on the right of the equation. But static friction has a less than or equal to sign to it. And this matters because now static friction can vary, and it can vary on the situation. So what does this equation give us? This equation doesn't give us how much static friction we have. This equation gives us the maximum value of static friction, right? For example, If I had a book on my table and I didn't push it at all, I wasn't even trying to move it, how much static friction would be there? None, because it's not opposing anything, right? If I applied a force of 1 Newton to it and it still didn't move, how much static friction is there? Well, 1 Newton, it's just enough to cancel out what I'm doing. So the acceleration's 0 and it doesn't move, right? And if I applied 5 Newtons, then it wasn't moving. Well, then I know static friction is 5 Newtons. I can go all day with this. Static friction is just enough to cancel out what I'm doing. So why do we calculate something? Well, we calculate something to give us the maximum value. And if we go higher than that value, that's when the thing we're pushing will break free and start moving, right? So if we're less than the maximum value, the object's going to stay stationary. If I go greater than the maximum value, then the object will start moving. And then once it starts moving, well, guess what? I don't even have static friction anymore. I have slide-in friction again, right? So there are two uses to these, and they're really used in two different situations. And when I calculate the static friction, I'm really calculating how hard do I have to push to get it moving. And if I'm anything less than that, it simply won't move. Slide-in friction is what's there while it's sliding. If I overcome that and I push more than that, it's going to get faster and faster and faster. If I push a force equal to slide-in friction, it's just going to keep on moving at a constant rate. And if I push less than that, well, then it's going to slow down and come to a stop. So they really have two different uses to that. Okay, so these are the other forces that we care about, two different types of friction. These are the equations for them. And if you look at the next videos with problems, you'll start to see how we calculate these things or how we use these equations to get information. And then once we have this information about forces, how do we determine what's going to happen to the block, right? Is it going to speed up? Is it going to slow down? Is it going to just keep doing what it's doing?